In this video, we will address the problem of the design of a digital modulator. We'll see that in general this problem can be difficult, but that the vector representation of signals can simplify notably the design process. The design of a digital modulator consists on the selection of M signals. M signals to be associated to the M symbols that we have in a M80 system. For instance, if we have a 480 system, when we have 2 bits per symbol, this means 4 symbols, 00, 01, 10, and 11. It is necessary to select 4 signals to associate each one of these signals to one of the symbols. But it's possible to select these 4 signals, for instance, or maybe these 4 signals here, or maybe these 4 signals here. Here, in this video, we will analyze the factors that must be taken into account in the selection of the M waveforms and how a vector representation of the signals can simplify the problem of selecting an appropriate set of M signals. The first factor to consider in the selection of the M waveforms is performance. At the receiver, the signal that is in every symbol interval will be compared with the M waveforms, looking for the most similar one. Therefore, it is necessary to introduce a measure of similarity to consider the probability of error. The higher the similarity, the higher the probability of error, because to avoid confusions, it's much better to have the signals being as different as possible, with the lowest possible similarity. Intuitively, a possible measure of the similarity between two signals could be the energy of the difference between these signals. The higher the energy of the difference, the lower the similarity. And it's possible also to introduce a square root here. Later, we'll see the reason for this square root. To increase the difference between the signals, to increase this measure of distance between signals, will reduce the probability of errors. The second factor to take into account is power or energy of the transmitted signal, because the energy is always limited in practice. And it's necessary to quantify the energy associated to every symbol, which is the energy associated to the different signals that are associated to the symbols. If we compute the energy for every signal, it's possible to define the mean energy per symbol as the average of the energy of the different signals that can be obtained, for instance, in the time domain by integrating the square modulus of the signal. And the third factor that must be taken into account is channel adaptation. It is necessary to take into account the response of the channel that is used to transmit the information, because the signals will be transmitted through this channel and will have the convolution of the transmitted signal with the impulse response of the channel, and of course we will have always the thermal noise. But the ideal situation at the receiver is to have exactly the same signal that was transmitted with thermal noise. Thermal noise is unavoidable, but at least we want to have only the addition of thermal noise. To achieve this, the frequency response of every signal must be matched to the channel to produce the same frequency response after the product with the frequency response of the channel. In the frequency domain, it's much simpler to see the condition that must be satisfied than in the time domain when we have convolutions. But this is equivalent to say that the convolution of every signal with the impulse response of the channel must be equal to the signal itself. In this case, At the receiver, we'll have just the transmitted signal plus noise. These are the main three factors that must be taken into account in the selection of the M waveforms. However, it is difficult to consider these three factors at the same time working with the signals in the time domain or in the frequency domain. Because, for instance, distance and energy have a trade-off. For instance, if we scale the signals here are scaled with respect to these ones, and then we have the distortion of the noise. The distance is higher, the effect of the noise is lower, but the energy is much higher. And at the same time, we have to take into account distance, energy, and the frequency response of the signals to fit the frequency response to the response of the channel. For instance, using baseband signals in baseband channels or bandpass signals in bandpass channels. As a summary, it is necessary to take into account in the selection of the waveforms the similarity or difference between the signals to guarantee performance, the energy of the different signals, and the adaptation to the characteristics of the channel. And in general, to consider altogether these three factors can be a difficult problem, at least working with the continuous time definition of the signals or with the frequency responses of the signals. However, this can be simplified by using a vector representation of the signals, because signals can be represented as vectors in a Hilbert space. And the idea is that with this vector representation, it is possible to isolate the first two factors, the similarity and the energy, from the third one, from the channel adaptation. And this means that the design will be simpler using this vector representation of the signals.